Resampling techniques. Resampling techniques are techniques that are used for estimating the performance of different machine learning algorithms. These techniques are especially helpful when we do not have a lot of data. Generally, a subset of samples are used to train a model, and the remaining samples are used for estimating the efficacy of the model. For a better estimation of a model's performance, this process is repeated multiple times and the results are aggregated and summarized. The differences in these resampling techniques are based on how the subsamples for training and test are chosen. The first method is called cross-validation. Cross-validation is an example of resampling techniques that allows us to compare different machine learning methods. A dataset can be repeatedly split into training dataset and a validating dataset. This is known as cross-validation. These repeated partitions can be done in various ways, such as dividing into two equal datasets and using them as training validation and then validation training, or repeatedly selecting a random subset as a validation dataset. To validate the performance of a model, sometimes an additional test dataset that was held out from cross-validation is used. This subset is called held out dataset. Cross-validation doesn't work in situations where you cannot shuffle your data. For example, in time series where times is important, so the sequence of data is important and you cannot shuffle them. So you cannot randomly pick different subset of data. Cross-validation gives a better, more stable, and reliable estimation of a model's performance than just a sample train test split by conducting several train test split and averaging over the result of predictions. Why use cross-validation? The accuracy score of a model can vary based on training dataset. To see this yourself, you can change the values of random state in train test split function in one of the examples that we have done so far, and then run the model. You will see the accuracy score would change each time you change the random state. This means that if you train your model on different part of the data and then test it on different part of data, you would get different results. Using multiple train test splits would give a more reliable estimation of a model's performance for previously unseen data. It would also give us information about how sensitive our model is to training data. K-fold cross-validation. In this method, samples are randomly partitioned into k different subsets of roughly equal size. A model is trained using all the subsets except one, which is used to make prediction and to estimate performance. This means that out of the k different subsets, k-1 is used for training the algorithm, and one set is used for testing the algorithm. This process is repeated each time with a different fold or subset for testing. Then the k resampled estimates of performance are summarized. This means that we're going to find the mean or the average performance of the algorithm over the k samples. For example, k equal to 5 and k equal to 10 are the most common used in the literature and in practice. Five-fold cross-validation. This is an example of a five-fold cross-validation. We divide our data first into five-fold here, equal sizes, as you see here. This is one fold, another one, the third one, the fourth one, and the fifth one. Then each time we pick one of the folds for testing and the rest for training. And then we repeat this multiple times. For example, in the second time, we pick this one as for testing and the rest for training. Next time we pick this one for testing and the rest for training. Next one we pick this for test and the rest for training. And last we pick the last one for test and the rest for training. Because we are training the same model on different data set, that means we kind of have different models. That's why you see model 1 here, model 2 here, model 3, 4, and 5 here. Because when you train your data on different subsets of data, you actually have different parameters set for your data. So at the end, we're going to average the performance of these models on the 5 subset or fold that we have here. That average would be the average performance of the model. A stratified cross-validation. In a stratified cross-validation, the samples are selected randomly to assign to each fold instead of selecting them in their own order, because there is a chance that classes might have been put in order, so our folds would be biased if we pick them in their own order. Let's see an example to make sense of all of this. Remember that we did a classification for fruits. We classify a fruit based on its weight, mass, and color, size, etc., etc. These are the example. So, as you see here, all of these entries are the class apple. All of the next entries are mandarin. All of the next are oranges. All of the next are lemons. So if we actually use normal cross-validation by order, for example, we pick the first fold as testing and the rest for training, then in our training data, there is no apple class. So the algorithm have not seen any apples before, so to speak. So when we test it, it will be shocked because it hasn't seen any apple. So that won't be a fair prediction or a fair training. It would be a biased education or training of our algorithm. That's why we're going to do this randomly. We're going to select, instead of by order, in their own order, we're going to select randomly for training and test to make sure that our algorithm has been seen all of the data and it's not biased. As you see here in stratified class validation, instead of going with order, we're going to randomly pick which fold for test and which folds for training. So here, for example, we're going to pick one apple for test one time. We're going to pick another fold here or data point here for test, another random for test, another random for test, and then we're going to assign the rest for training. So in this method, as you see here, our test data actually has seen apple, mandarin, orange, and lemon, all of them. And it means that we have educated our algorithm well. It's not biased. Scikit-Learn uses a stratified cross-validation for classification, but it uses normal cross-validation for regression problems, since the issue does not hold true for regression problems. Leave one out cross-validation. In leave one out cross-validation, each single sample of data is considered as one fold. The testing fold only consists of one single sample or data point. This is particularly useful when we lack data, when we do not have a lot of data. Let's see a visual example. So here we have our whole data here. We have n data points or n samples. So what we are going to do, we are going to create n different models here. And in each diff model, we're going to pick only one data point as test. For example, this is the first fold for test, and the rest is going to be for training. For the next, this one is going to be for test. This is just one single data point, and the rest that are colored in blue are going to be used for training. Next one, as you see here, the third sample or data points is going to be used for training, for test, and the rest is going to be used for training. And so on and so forth until we actually have picked all of the data points for test, as you see here. The reason that we do this is, again, because of lack of data. So our fold or our test actually data set would include only one single data point. At the end, we're going to average the performance of our algorithm over all the n sample data points that has been assigned for test, or the average performance of the n models. Using cross-validation in Scikit-Learn. To use cross-validation in Scikit-Learn, you need to import it first. The function is called cross_val_score, and it's in the model selection module in Scikit-Learn. Then what you need to do, you need to call the model to the function and then import your model, then the feature variable and the target variable. This is going to generate different evaluation score for your model. For example, if you use a 5-fold cross-validation, this is going to give you 5 different evaluation score based on different models that have been trained on different parts of data and test on different part of data. The default for the number of folds is 3. So if you want to change this, you have to set the CV, which is cross-validation parameter. Let's see an example here. So here, the cross-valid score, you're going to give it your model and then specify the independent variable and the target variable, and then you can actually tell me, I want to have 10-fold. This is going to generate different subset using the stratified cross-validation and train your data and test your data based on different subset or folds of your data. And it's going to generate 10 different models having been trained and tested on different data. And then it's going to give you the 10 evaluation scores. You can print out the cross-validation score computed here, assigned to this, for example, as follows. Print cross-validation scores and then the name of the variable. You can also print out the average performance using the average score by using the numpy mean function and then give it all of the cross-validation scores. Validation curve. Sometimes we want to see the sensitivity of a model to changes of an important parameter. In Scikit-Learn, we can use validation curve to see the impact. First, we need to import validation curve function from model selection module in Scikit-Learn. Then we're going to define the ranges of the parameter that we want to study, whatever that is. Then, because we are using cross-validation for this, we have to define the number of folds in cross-validation. For example, if I want to have 5-fold cross-validation, I define CV as 5. This is later is going to be used in validation curve function here that we are going to feed in the model that we study, the feature variable, target variable, the parameter names, whatever it is that you want to study, and then the range of parameters. And last, we set CV, the cross-validation number of folds, to CV that we define here as 5 or whatever else. And we assign these to two values here, train scores first and test scores second. These are going to be the two outcomes of the validation curve function. So the validation curve function is going to do the process of cross-validation, the CV-fold, which here is 5-fold cross-validation, based on different ranges of the parameter that you study and the ranges that you have defined. And then it's going to output the score for training and test dataset. You can actually plot these scores in a graph. Let's see an example of an application of validation curve function in KNN algorithm. So we want to see the sensitivity of the performance of KNN algorithm based on different values for K, the parameter K, which is number of neighbors. So we're going to first define the values for different K values, the parameter range here. So this is just a list of the values for k, the number of neighbors, k equal to 2, k equal to 10, and k equal to 20. So this is our range for number of neighbors. And then we're going to use the validation curve function. In the validation curve function, we're going to input our model first, then we're going to input the feature variable and the target variable, and then the name of the parameter that we want to study, which is the number of neighbors, or k. And after that, we're going to set the parameter range into the parameter range that we defined here. So what this does is actually creating a threefold cross-validation. The number of fold k here is 3 by default if you don't change it. And find different values, the accuracy score, both for training and testing for each different cross-validation, and also for different parameter range. And it's going to import it to these two values, the test scores values and the train scores values. Then we can actually print out these values. So here we have three values for the range of parameters, and also we're going to use the cross-validation, a three-fold cross-validation. So that means we have 3 multiplied by 3, which is 9, scores for training, and 9 scores for testing. So for example, these three are the output of the 3 cross-validation for parameter 2. Parameter number of neighbors equal to 2. The second values, these three, are the output of the cross-validation score for the training for when k is equal to 10, the number of neighbors is equal to 10. And the last three values or scores here are the training accuracy score based on the threefold cross-validation of when k, or the number of neighbors, is equal to 20. Similarly, we would have 9 different accuracy score for test. So for each actually parameter, we can find the average of these accuracy score and plot them, as you can see here. So in the graph on the right, the y-axis shows the accuracy score, and the x-axis shows the k, different k, or the different values for parameter k, the number of neighbors. The average cross-validation accuracy score for training data is shown by this solid orange line here that you can see here. The variation for these values is actually shown by the shaded area, the small shaded area around this solid line. For the training data set, this is shown in orange color. And for the test data set, it's shown by this solid blue color. Also, the variation is shown by the blue shade color here. So this variation curve shows the mean or cross-validation accuracy score for training and test sets as a function of k, the number of neighbors in KNN algorithm in our example. It is important to remember that cross-validation is used to validate or evaluate a model, not to tune parameters here. To tune parameters here, for example, we can use the validation curve as you see here. So for example, it looks like that this point right here is the maximum accuracy score for test data, which corresponds to 10, k equal to 10. So the best value, the optimal value for k is actually equal to 10 here. Another method of resampling is bootstrapping, that we have seen it before. The idea of bootstrapping is the same as what we have seen in random forest. A bootstrap sample is a sample of the data taken randomly with replacement. This means some data points might actually be selected more than once, and some data points might be not selected at all. The latter data points are called out-of-bag samples. That's those samples that have not been selected at all. Those are called out-of-bag samples. Models can be trained on bootstrap dataset and then tested on out-of-bag samples that the model has not seen before. So suppose this is our original data. This is just in visual that you would better understand it. So we have different color and different shape here. We have circles, we have cubes, etc., etc., and also different color. We have orange, we have green, and blue here. So in total, we have 12 different color and shapes here. So let's do a bootstrapping here. So the first row is the number of bootstraps, and then we have the train model here in the second column, and the third column we have the test model. So we're going to actually make a bootstrap dataset and use that to train our algorithm, and then we're going to use the out-of-bag sample for testing. So for example, we're going to build a bootstrap here right now. This is our bootstrap. So this is again 12 shape, but not all of them actually are different. For example, we have picked 2 plus 1, 3 blue circles, 2 red squares, and 2 orange this shape. This means that we have left out 4 different shape and color that has not been used. Those are the out-of-bag samples. The out-of-bag samples are these shapes and color that we don't have it in the training model, and we're going to use it for testing. So let's build another bootstrap dataset. So we're going to pick 12 times we're going to pick one shape out of these 12 different shapes here. Some of them were going to be repeated, and some of them not going to be selected at all, which is going to be our out-of-bag samples. So let's pick 12 different or 12 times selection of these shapes. So here we have selected 2 green circle and 2 red squares and 2 red of these shapes. This repetition means that some of the data or shapes have not been selected at all, or the out-of-bag. We're going to put that or assign that for testing. These shapes and colors have not been used in the training. Right, let's take a look at another example of bootstrapping. So we take again 12 data points or 12 shapes here. Again, as you see here, some of these shapes are repeated. For example, we have 1, 2, and 3 of these shapes that are the same color. And we have 2 of these shapes that are the same color and shape. So this means that some of these original shape have not been selected at all, the out-of-bag samples. We're going to put them or assign them for testing. These shapes that you see here have not been selected at all.